Okay,
Yeah.
looks great. Perfect. Actually, in fact,
Perfect.
you can just leave it there if you want, and we'll start back again in a minute.
Okay.
Should make sure that the conference room is also ready. So yeah, Shuang-Yong, if whenever you guys are done with the coffee break, you can let me know and we'll
Yeah, we are
start.
back from the break.
You're back. Okay. Great. So let's start for the second half of this session, where we're going to get a little bit more information on the global picture and then some more dedicated insight on how to maximize sensitivity to some of these operators in LHC data. So we start first with Giacomo Magni, who will tell us about another SMEFT result looking at vector boson scattering and Diboson data. So please go right ahead.
Okay, good morning, everybody, or good afternoon, and thank you for inviting me to this talk. Today, I would like to present you our results on the analysis on VBS data and Diboson data from the LHC in the context of the standard model effective field theory. In particular, I'm going to show you another SMEFT standalone study based on the publication we had in January with Jake Hater, Raquel Gomez-Ambrosio, and Juan Rojo. Our goal here is to understand the interplay between the VBS data and the Diboson data in a dimension 6 effective field theory study, and in particular to try to do a quantitative analysis of the impact of the VBS data when doing a fit together with Diboson data to constrain the Wilson coefficients. This study can be considered the first step towards the inclusion of VBS data in a global fit together with the Higgs, top, and Diboson data, as in the talk we saw before. Let me recap a bit the theory settings that we have. We expand the standard model Lagrangian to include the linear dimension 6 operator from the worst of basis. We include only bosonic operators, since we are going to discuss about processes in which the electroweak bosons play a crucial role. And we do have a two fermions operator. They can modify the interaction between vector and the fermions, and we also have a purely bosonic operator modifying the interaction between boson themselves. And for instance, I'm going to point out that there is just one operator, CW, able to modify the triple and the quarti-gauge coupling, as you can see in the Feynman diagram. In particular, in VBS, there is also the possibility to access the quarti-gauge coupling, which is a unique feature of this process. And also VBS can be mediated to an exchange of an Higgs field in a sort of T-channel. And those diagrams are the most interesting one when looking at the EFT effects. For the time being, we do not account for a quadratic term in our analysis, but we allow for CP violating operators, the one labeled with a tilde. In our analysis, we had 70 experimental data points split in 52 coming from the Boson data, a fiducial and differential cross-section from Atlas and CMS run 2, and then 18 fiducial and differential cross-section from VBS, also from Atlas and CMS. All the vectors in all the channel are decaying leptonically. This is mainly due to experimental reasons, but of course we are open to analyze also other possibilities in the future. When there was a background, we simulated the EFT only in the signal region, and this is especially true for the VBS, in which we account for the EFT interference term only in the pure electroweak components of the measurements. In VBS is a process proportional to alpha electroweak at the power of 6 leading order, in which you have 6 particles in the final states. Among them, there must be 4 leptons and 2 of them charged. And this characterized by the 2 jets with a huge separation in rapidity higher than, for example, 2.5, and a huge invariant mass higher than 100 of jets. This cut results in a low cross-section, which is around 1 femtobar in the fiducial phase space. On contrary, in the Diboson production, jets are produced by QCD soft interactions, and so are modeled with Parton shower in our analysis. In Diboson production, you also have 4 leptons in the final states, and you can select some cuts on the transverse momenta and the missing energy if you do have neutrinos in the final state. In this kind of processes, gluon fusion might be relevant to reconstruct properly the experimental measurement. In the slides on the right, you see 2 differential distribution, one from VBS on top and one from Diboson, opposite sign WW, compared with the experimental results from data and CMS and our theoretical prediction. We start our theoretical calculation simulating some Monte Carlo events for the standard model with MADGRAPH and POECBOX at next to leading order. We then add the HEFT linear contribution at leading order with a SMEFT SIM UFO model, assuming as SU35 symmetry. We then perform Parton shower using PTI8 in order to model properly the jets, and we select the experimental phase space with a rivet analysis that we wrote specifically for each experimental dataset. Finally, we collect our experimental data from HEFT data with the corresponding uncertainties. Here, we show you some sensitivity plots in which we compare the standard model theory with the standard model plus the HEFT, assuming that the Wilson coefficient has a reference value of 0.5. As you may expect, you can see that the HEFT effects are bigger in the high tail of the distribution, but depending also on the process, you can have an effect in the bulk of the distribution, justifying that when you do such a fit of the Wilson coefficient, it's really important to include the differential cross-section compared to fiducial cross-section. Our fitting strategy is based on this toolkit called SMEFT, which Luca just presented in the talk before. We define our figure of merit as a standard chi-square, and we include in our covariance matrix for all the experimental uncertainties and available correlation, and also for some theoretical uncertainties coming from the Monte Carlo and the PDFs. We then perform a Bayesian reweighting, sampling the posterior probability with an algorithm called nested sampling, assuming that we have a multi-Gaussian likelihood, which is proportional to the exponent of the minus chi-square, and a flat prior, which is assumed to be an hypercube in the space of the Wilson coefficient. The first quantity you might look in a fit is, of course, the chi-square. On average, we managed to reproduce our data set with a good accuracy also in the standard model hypothesis only. However, we observe some statistical fluctuation when looking at the VBS fiducial cross-section, and this might be due to the lack of statistics. So we expect that the chi-square will even improve when more VBS points will be, experimental points will be available. And then the chi-square is naturally reduced by the algorithm of minimization. Another interesting quantity to quantify the effect of each channel in a constraint one Wilson coefficient is the Fisher information, which is basically defined as the ratio of the standard model effective field theory contribution divided by the experimental uncertainties at the power of 2. In the table here, I show all the values for our 16 degrees of freedom, and you can see that the 2 fermions operator, which are the one listed in the top part of the table, are basically constrained from the Diboson data. Instead, the VBS data start to play a role when you look at the purely bosonic operator, which are the one listed in the low part of the table. Here, I want to stress that the constraint on CWWW, the operator modifying the triple and the quartic-gauge coupling, are coming also in this work from the Diboson data, and this is consistent with the previous talks. In this slide here, I show the posterior distribution, so the fit outcome for our baseline Diboson plus VBS. On the left, you can see the posterior distribution of our 16 degrees of freedom. They all look Gaussian, so there are no flat direction, and this is expected from a linear fit. While on the right, you see 95 confidence level bounds and central values for 3 different scenarios. In blue, a fit including only Diboson data, in orange, Diboson plus VBS, and in green, the individual fits that you can obtain when fitting one Wilson coefficient at the time. Clearly, our constraints are coming mainly to the Diboson data, but there is a small but consistent impact on the VBS from the VBS data, testifying that they do carry some additional information. Moreover, adding the VBS data to our analysis permits us to fit 2 additional coefficients which are not constrained by the Diboson data, which are CPB and CPB tilde. A useful tool that you can use to deepen the understanding of the correlation between the Wilson coefficients are the 2-dimensional fits. And you see here some 95 confidence level bounds. And you can see how the ellipses from a different selection of dataset, VBS and Diboson, do not overlap completely, testifying that VBS data carry some slightly different information from the Diboson. In particular, you can see the effect on the operator CPB, which is not constrained by the Diboson. In order to deepen our understanding of our VBS fit, we try to hire our statistics, including also some detector level events. We could include only bins with high statistics, namely the one in which there were events higher than 30. And we include some 2 different data sets, one from CMS ZZ-JJ production, and the other one Gamma and Z production associated with 2 jets from Atlas, for a total of 15 more data points. This way, we managed to break the degeneracy that we were seeing on CPB and CPB tilde, as you can see in the posterior distribution. And you see that on average, this improved a lot our constraint coming from a VBS only fit, and all the Gaussian distribution shrinks to the central value, which is a consistent picture, and testify that what we are lacking in this study is basically the statistics on the VBS data. Finally, we performed a toy model for high luminosity LHC, in which we randomize our theoretical prediction, adding some Gaussian noise proportional to the systematic and statistical error that we assume will be there in high luminosity LHC, which is roughly the 50% of the systematic that we have right now, and 80% less than the statistical that we have right now. We assume the same LHC binning of the distribution that we used in the previous fits, and we simulated the 61 data points in electroweak VBS only, meaning that we assume that in the future we might be able to separate and disentangle completely the electroweak signal from the QCD background in a VBS measurement. On the right, you can see 3 different scenarios. In blue, the VBS only results from our fit, using the current data. In orange, our baseline Diboson plus VBS, and in green, the result of this toy model. There is a huge impact going from blue to green, testifying that in the future, VBS measurements might be competitive in a dimension 6 EFT study, and may also challenge the accuracy that we see right now from the Diboson data. In conclusion, with this analysis, we show that VBS data are complementary to the Diboson data when looking at dimension 6 EFT operators, and we perform a quantitative fit comprehensive of all the experimental data on VBS available right now. Of course, this is just a first step, and there are a lot of approximation we would like to improve. From the theory side, we would like to add dimension 6 quadratic terms, which might be important also for theoretical reasons, such as the unitarity. We would like to add also some next to leading order effects in the EFT and compare with the dimension 8 operator, which are the most studied in literature so far on VBS, and perform a coherent expansion of the Lagrangian to the order of lambda to the -4. From the fit side, instead, we might add other channel, for instance, single boson production and electroweak precision observable. And in the future, we might be able also to study a rare effect as the polarized VBS, which is so far covered by statistical uncertainty. And for that, we would like to add the possibility of fit a Poissonian likelihood to model properly the low statistics distribution. Yeah. Thank you for your attention. And if you have any questions.
Thank you, Giacomo, for that nice overview. So let's open the floor to the conference room for questions.
I have one question. Yeah, thank you. And yeah, exactly on this page, you said future improvements. And at the last point, you said compare with the dimension 8 operators. So VBS process is a bit special, right? Contains the various diagrams, and dimension 8 could be, already from the part of the diagrams. Do you plan to combine dimension 6 quadratic term altogether with dimension 8 interference in your future study?
Yeah, our fit tool permit to do that because it's really powerful in this sense. You just need the theoretical prediction, which of course are not really are the most challenging stuff to obtain because the calculation are quite long for VBS. We saw that there was an improvement in MADGRAPH and there are a lot of operators to consider. So doing the calculation is the most challenging part for including dimension 6, dimension 8 and dimension 6 quadratic terms. But then from the fits code, we are okay, and we will be able to fit them together, we think.
Okay, thank you. I don't see any other questions in the room.
Okay, what about from our online participants? Oh, yes, I see a hand from Mike.
Just a quick comment on what the speaker just said. In terms of the calculation has essentially been done for many of the vertices up to dimension 8 that feed into your predictions. There's just the 4 vector vertex where there's a little more work that needs to be done. But I think if you look at the fact that the dimension 8 operator basis has been defined, for example, in the paper by Chris Murphy, I think the theory side is actually at this point defined out to dimension 8 for this process. It's just a matter of it's not in code.
Okay. Yeah. Okay. That's cool, and we are looking for it. So.
Céline.
There was a measurement of VBS, but not to 2 boson, but to 1 boson. So VBS going to a Z, which was showing slight CP violating tendencies being used for discussing EFT contribution to the thing. So since you're including those CP violating operators, I was wondering if there were any plan to introduce also this kind of data in which you have a VBS but just one single Z boson produced. And that might be especially interesting for you CP violating operators.
Yes, this is definitely true. ZJJ or WJJ production is on top of our to-do list for the next updates. And of course, we are thinking about keeping the CP odd operator also in the future updates, because when you add the CP odd operator, you may also want to consider some specific observables, which are not just differential cross-section. So we are thinking on it, and we'll see. But for sure, single boson production with 2 or 1 jets will be included in the future.
Okay, thank you very much.
All right. If we don't have any final questions, let's thank Giacomo again, and we can move to the second talk of this session.